Welcome everybody to my talk about fast radio bursts and how we can use them to learn something about the large-scale structure and baryonic feedback. My name is Reischke, and if I don't work on fast radio bursts, I'm at the moment mainly involved in the kilodegree survey working on gravitational lensing. Before we jump into the talk, I would like to thank the organizers for giving me the opportunity to speak here, and especially for keeping this really nice format alive even after Corona. So, what are we going to talk about today? First, I would like to give a brief review and introduction to fast radio bursts, and I will then talk about how we can use them to establish something like a distance scale similar to supernova measurements. And then I want to talk about the effects of the large-scale structure on fast radio burst observations and how we can leverage those to learn something about baryonic feedback and hence also about our cosmological model. So let's dive in. What are fast radio bursts? So the mechanism is very much unknown and still under debate. However, they were first discovered in archival data in 2007 by pure coincidence. And the name, what they are, kind of says it all. They are short, they are bright, and they are radio transients. The frequency usually ranges from a few hundred megahertz to several gigahertz. And since they are so bright, they can be seen over extragalactic distances. Up to now, we know roughly 600 events. However, soon there should be several thousands with upcoming surveys, but also with ongoing surveys who have now dedicated searches for them. Also, some of them might be repeating, which sheds some light on proposed mechanisms, which are nicely summarized in the Living Theory Catalog for Fast Radio Bursts, which has a wiki page and is a summary of all current theories. And if a theory is basically ruled out by data, it gets checked off the catalog and is ruled out. Some of the prominent theories are neutron stars, mergers, or magnetars. Let's now talk about the known FRBs. I've brought you a picture here of some of the known FRBs, so they are basically all over the place, as you can see. And not necessarily associated with the galactic disk. Until now, the detection is mostly incidental. However, in principle, you would expect rates of several thousand each night on the whole sky. And there are ongoing dedicated searches now for FRBs, which is CHIME, and ESCAP, which is the precursor for SKA. So let's look about how fast radio bursts actually look like. So I've brought you here a plot from actually the very first fast radio burst, which was discovered in this archival data. And you see here the arrival time, and here you see the frequency band. And what you can also see is that the burst, basically this dark line here, is dispersed. So it arrives at different times in different frequency bands. If you divide this dispersion out, you get this here. So this is the original burst. And this pulse delay is basically a typical 1/frequency squared scaling, which comes from the scattering of the photons as they travel through the intergalactic medium to us. They scatter at the free electrons, and therefore this dispersion measure, the proportionality constant to this proportionality here, is a measure of the integrated electron density along the line of sight. So let's look at the different contributions to the dispersion measure in more detail. First of all, we have the Milky Way component here. This is very easy to measure, or relatively accurately measured by pulsar observations. Then we have the large-scale structure contribution, which is most of the time by far the dominant contribution. It just comes from the travel through the intergalactic medium. But then you also have, depending where the fast radio burst goes off in its host galaxy, you have a host galaxy contribution. Luckily for us, these contributions have different redshift scalings and can therefore be separated statistically. If we have a lot of FRBs, especially if we know the host, so if we have an independent measurement of the redshift, we can tell these contributions apart by just using statistics. So the most important part for us here in this talk is the contribution from the large-scale structure. So let's look at it in a bit more detail. So I copied the equation here. And let's look at the different ingredients. So we have the electron density, and we split this up. So you get a contribution from the density field, of course, but you also get a contribution from the ionization history here. And you have the contribution from the background density, and you have a distance measure here. So that's why as I will show you, you can use this as a distance scale. Rho B here in the front is the baryonic fraction, and these things, in order to evaluate those, so the distance scale, the ionization history, and the baryonic density, we need redshift. So we need a host identification of the fast radio bursts. However, if we are only interested in the clustering of the dispersion measure, so the statistics, the angular statistics of the dispersion measure, we don't necessarily need the redshift. So we don't necessarily need a host. We can just use the fast radio burst itself. So let's now come, after this very brief introduction, to the distance scale. Let's go back to the large-scale structure dispersion. So we calculate the mean large-scale structure dispersion. The electron density can then be approximated by the mean ionization and the mean baryon density. MP is the proton mass. And if we rewrite this a bit, we arrive at this equation here. And if we assume full ionization, which should be valid below redshift 1, we get this measure here, and we integrate from 0 to z. And therefore, this is a measure of the expansion history, very, very similar to the supernova MA measurements. So on the background level, however, there's a perfect degeneracy here between H0 and the density of baryons. However, if we combine this with a prior on the baryon density from CMB or Big Bang nucleosynthesis, so which actually measures the physical baryon density, which is capital omega B times H squared, we can get constraints on the Hubble constant. However, as I said, we need the host identification for this. So there are dedicated FRB surges from radio arrays, and they have very, very long baselines, and therefore they have excellent angular resolution, which actually helps you to identify the host galaxy. And here I brought you an image from this paper, which used VLT plus ACAP observations, and you do basically optical follow-ups in the host galaxy. So, and then you can identify by spatial coincidence the host of the fast radio burst, and you get automatically an independent redshift estimate. But if you have this, you can plot such a diagram, the dispersion measure redshift diagram, and we have all the data here. And then you can fit basically the dispersion measure contribution from the background to this line, and you can infer by the slope the Hubble constant if you add a Big Bang nucleosynthesis prior. And what you get out is basically this here. So this is the posterior distribution on the Hubble parameter. And what we see is that events at large Z are most important. And the error is mainly dominated by the uncertainty of the host contribution. But if you combine all these radio bursts I showed you in the previous slide, we get this constraint on the Hubble parameter, which is, of course, at the moment not really competitive with CMB or with shoes. However, if we get more FRBs with host identification, this will increase. Just for comparison, this is what you can do with gravitational waves. So when can they be competitive? And what I show you here is the uncertainty on H0 as a function of the number of detected fast radio bursts with host. And if we have a few hundred, we can get a measurement on H0 at the precision of roughly 1%. The next question you can ask is, can we relax some assumption with a larger sample? So can we, for example, simultaneously fit also for the host contribution? And the answer is yes, we can. So if you have 500 events, you can determine the host contribution and the Hubble constant simultaneously. So here we have the host contribution and the Hubble constant. You still get a very, very nice measurement on the Hubble constant, even though you leave the host contribution completely free. So now we have investigated basically how we can use the background component of the dispersion measure to learn something about the expansion history of the universe. However, the electron distributions follows to some degree the large-scale structure in the universe, and therefore you also expect some clumpiness in the distribution. And can we measure and take into account this effect as well? So now for this, consider you have two FRB observations, maybe with host, maybe without host, but let's assume that they are identified with the host at the moment. Therefore, the events will be traveling through the same large-scale structure in this way. Therefore, nearby lines of sight are correlated. So the dispersion measures of these events are correlated, and you need to take this into account, which you did in a recent paper, where we did basically the analysis for the Hubble constant with the known FRB sample. But as you can see here, the correlations are very, very small. Since, well, if they are very far apart, they basically don't travel through the same large scale structure. However, if you have more FRBs, not only the 10 we had in the previous analysis, if you have a few hundred FRBs with host identification over the whole sky, you can see here the 1 sigma error band basically on a fit of the Hubble parameter, and the orange contour basically shows you what happens if you take a diagonal covariance only, and if you take the full correlated events into account, you get the blue band. And you can see that if you have a few hundred FRBs, there's a significant difference between the two, and you tend to underestimate the error. So you need to take this into account in the future. At the same time, the covariance also contains cosmological information, right? Because it itself depends on the cosmological model. If you have, for example, more clustering, then you have a larger uncertainty on your dispersion measurement. And that's what's basically shown here. So if you assume that the covariance does not depend on the parameter, in this case, H0, you get a wider posterior distribution. But if it depends on the parameter, it narrows a bit because you add some information to this measurement. What you can also ask yourself, for example, if you have this dispersion here, do we get an additional dispersion, for example, from breaking of the equivalence principle? And what people have done so far, if you have a breaking of the equivalence principle, you get an additional gravitational delay due to the equivalence principle breaking, just because different photons travel differently at different frequencies. And so far what was used was the standard classical Shapiro delay expression. However, there's in principle a problem I will come to in a moment too, but the idea is that you put an upper limit on delta gamma by just measuring for individual line of sights this delta T graph by assuming some model for delta T dark matter or for the dispersion measure itself. However, adding structures will just increase the limit monotonically, and the cosmological setting, this standard expression for the Shapiro delay just doesn't make any sense because it's not gauge independent, diverges due to the Brownian conditions. So what you should rather use is a fluctuating gravitational time delay, where you have the Newtonian potential here. The problem now is, of course, that the fluctuations in the time delay can be positive and negative, and therefore setting an upper bound is no longer sensible or possible. So what you need to do is you need to take into account the correlations of different dispersion measure signals, basically what I just discussed in earlier on the earlier slide. And what you basically do is you allow a delta T graph between different frequencies to be dependent on the frequency, and then you measure basically a contribution here. And if you do that, what you can see is, I show you here the correlation coefficient. If you don't have equivalence principle breaking between the fast radio bursts I showed you before and which we used in this analysis here, and now you turn on the equivalence principle breaking term, and what you can see here is you have huge correlations between these different FRBs. And you can then leverage this effect to constrain the breaking of the equivalence principle in a very low energy range, which has not been possible in a consistent way so far. And these are the constraints you find. So what we fit is basically you fit the dark matter host dispersion measure. I said dark matter now, it's always dispersion measure contribution. You fit the amplitude of the homogeneous component, and you fit this equivalence principle breaking term. And these are the most stringent constraints you find in this low energy range so far. So now we basically use the covariance of the measurement as a source of information. But in principle, nothing stops us of using FRB statistics so that we measure 2-point statistics of the dispersion measure correlation. And the nice thing about these 2-point statistics is basically that they are kind of weak lensing on steroids, because the signal is larger than the noise. And the noise comes that we just don't know the size of the host contribution, which adds an intrinsic noise fluctuation. However, they are still sparse. So why is this interesting? So one of the main issues in upcoming surveys is that we don't know the size of baryonic feedback. And this is a plot here which shows basically the total matter power spectrum divided by a power spectrum where you only have dark matter. So you have no baryon interaction, you have no AGN feedback, and so on. And I vary the strength of the feedback in this color bar here, and you see that you get significant changes in the power spectrum, which future surveys such as Euclid and Rubin LST want to measure to a few percent. So in order to be able to do that, you need to calibrate this feedback stuff very, very accurately. And maybe we can do this with fast radio bursts, since, as I just showed you, they are a projected quantity of the electron power spectrum. So using the baryon power spectrum or the electron power spectrum and cross-correlating it with gravitational lensing should give us very, very tight constraints on baryonic feedback, and hence also on other cosmological parameters. And at the moment, I have a master student working on this, Dennis Neumann, and these results are preliminary, but here is a fit to a cosmological model with a Euclid-like survey, where the Euclid constraints from cosmic shear only are shown in blue. And if you add fast radio burst in the mix, what you see here is, and I want to pull your attention on this last line. So first of all, you measure this AGN temperature, so this feedback strength parameter, very, very accurately using the fast radio burst in conjunction with the weak lensing measurement. But in particular, you also improve the measurement of the mass of the neutrinos by a factor of 2. And the reason for this is basically that they have an effect on the power spectrum very, very similar to the AGN feedback itself. And you can use the fast radio burst to break this degeneracy. So I'd like to summarize now. So the mechanism of the burst is still unknown, but they can provide an independent measurement to the Hubble constant, which has roughly this value. So it's not competitive at the moment, but we are getting there in the future. Currently, we are limited by statistics, but we will get many, many more events. Also, I showed you how correlations between different events allow you to constrain fundamental physics, and how you can, in the future, use these correlations to actually constrain baryonic feedback and to help Euclid and LSST to become basically the instruments they were promised to be. And with this, I would like to thank you for your attention.